The last part of carbohydrate is gelatinization and retrogradation. These are the learning objectives for this part of carbohydrate. You should be able to define starch granule, classify the different type of starch, describing gelatinization as well as retrogradation, defining modified starch, and also explaining the different type of modified starch, explaining formation of microcrystalline cellulose from cellulose, and lastly listing the different types of gums and also their application. Starch granules are made of amylose and amylopectin, and we have covered the difference between these two and the characteristic in the previous lecture. Now the shape of the granules are different. Okay, some will be spherical, some will be angular, some will be oval, depending on the species of the plant and also the maturity of the plant. And if you look in the figure below, like potato here, it has oval kind of starch granule. And then for rice here, the shape is angular. Whereas for wheat, the shape is more to spherical. And then in terms of the size of these starch granules, they are in the range of 1, which are the smallest for the case of rice granules, okay, 1 to 9 micrometer, and then it can be as large as 100 micrometer for potato. And then for maize, it can be in small size, about 1 to 5 micrometer, and then and for the big size, it can only go up to 15 to 20 micrometer in size. So we have covered these two different structure of starch, okay, which is amylose, straight chain of glucose monomer linked by alpha 1 to 4 glycosidic link, okay, whereas amylopectin is straight chain as well as branching at alpha 1 to 6 glycosidic link. Unlike monosaccharide and disaccharide, which are very soluble in water, starch do not form this true solution, but they only form temporary suspension when stirred in water. Okay, for example, you try to take the corn flour, okay, corn flour, and then you try to dissolve it in water. It looks as if it is soluble, but instead it's actually forming a temporary suspension because you stir the mixture of the corn flour with water. But if you left it to stand, you will see it will separate. Okay, it will separate. So that actually shows that it is not soluble, okay, in water. Now, for natural starch, they are mixture of amylose and amylopectin, in which the composition of the fraction or the ratio between the amylose and amylopectin in the plant differ depending on the species. Okay, for pure amylose but not natural kind of plant, they will only constitute about 70% of the amylose composition. And then for waxy maize starch, the composition of is dominated by amylopectin, which is about 90%. So this table here shows the starch composition in different type of starch in terms of the percentage of amylose and amylopectin. Okay, so for rice, okay, the amylose is only about 17%, and then the amylopectin is 83%. And for high amylose starch, the highest percent of amylose is about 70%, and the remaining is amylopectin. If you see in this figure here, for normal starch, the ratio between amylopectin to amylose is 3:1, means the highly branched composition is more compared to the straight chain of amylose. Okay, that is for normal starch. Okay, the amylopectin content will dominate. For waxy starch of plum, which is 100% amylopectin, you only see the granules exist as branch amylopectin. For high amylose starch, okay, it can go up to 60 to 85% of amylose. The composition of amylose is more compared to amylopectin, and this only exists in mutant grains, okay, like wheat, maize, rice, barley, okay, the mutant type. Now, when we look at the starch granule, okay, it has the crystalline and non-crystalline region. Okay, so the amorphous region here, okay, normally is contributed by mainly amylose, whereas the crystalline region here is contributed by amylopectin, which is about 30% in composition. Okay, so you see this spaces here is more compared to the one line here. We use different color. Okay, line only have this. Okay, this portion here. So this one is smaller in content compared to the amorphous region. Okay, the spaces between the lines. So undamaged starch granules will have this characteristic here. First one is insoluble, okay, in cold water. Secondly, no adhesive power. And thirdly, no binding capacity. Now, to have that three characteristic, which are soluble in cold water, having adhesive power, having binding capacity, the starch must undergo heating. Okay, so this figure here shows, okay, the slurry, okay, starch slurry granules. Okay, and this is what happened to the granules when you heat them up in the presence of water. Okay, it becomes partially swollen because it absorbs water during the heating stage. And then finally, when it becomes more swollen due to the water entering into the granules, it will burst. Okay, so it bursts, therefore it becomes gelatinized granule. So this process is called gelatinization. Okay, the disruption of molecular order within the starch granule. So it is no longer in angular or spherical or oval shape. Okay, it becomes disrupted. Okay, so that is gelatinization. Okay, now the evidence for the loss of order includes irreversible granule swelling. Means once it swell, uh, it cannot go back to its natural state of the starch. Okay, loss of birefringence. We'll look into detail what is birefringence. Loss of crystallinity and starch solubilization. Okay, following gelatinization is called pasting. So it involves granular swelling, exudation of the molecule component from the granule, and then eventually the total disruption of the granule. Okay, and that leads to the formation of the starch paste. Okay, so these two figure here, okay, the first figure here, okay, shows the unheated starch granule. Okay, under polarized microscope, okay, we can see it has this cross formation. Okay, something like cross formation here, as you can see. Okay, multis cross formation, and this we call as birefringence. Okay, means the light is refracted in two direction. The light is refracted one direction here, another one direction here, another one here. Okay, that's why you observe this multis cross formation under polarized microscope. This is what we call birefringence. Now, when the starch granules are heated and it lost its shape, okay, of the granule, okay, the oval shape or the angular shape, okay, it lost its multi-cross formation. Okay, and this is what happened under microscope. Okay, not what happened, what we observe under microscope. Okay, gelatinization involve granule swelling in water in the presence of heat. Okay, so that means it will lose its birefringence, okay, due to the structural change of the starch granules, okay, and leads to the loss of hydrogen bonding between the starch molecules and result in the formation of hydrogen bonding with the water. And some will leach out of the starch when it bursts, and that leads to increase of viscosity. So that's why when you dissolve, let's say sago flour in hot water, okay, eventually it will form gel or paste kind of structure. Okay, so this is where the viscosity increases. Okay, if the Melanau people are familiar with linut, so that's what happened when the sago starch undergo gelatinization. So heating will cause water absorption by the amyloplast or the starch granules, okay, followed by the rupturing of the amyloplast, which leads to the formation of starch network. And the point where the amyloplast ruptured is called gelatinization. Now, when we explain in terms of molecular, what happened during gelatinization, okay, when you supply heat, okay, it will leads to more vibration of the atom. So when the atom vibrates more, eventually it will break the hydrogen between them, okay, and then it will form hydrogen with the water molecule, okay. So the water trapped inside the starch granule will increase in terms of viscosity when it rupture, okay. So during the cooling period, okay, gel will form, which indicates formation of hydrogen bond between the water molecule and the starch granule. Okay, so this figure shows what happened to the starch granule. So this is the initial stage when it starts to become swollen, when it is heated in the presence of water, and then it will collapse, okay. Once it cools down, okay, the water will be in between the, okay, in between the starch granule. So this is the point where we call starch gel, okay. Hydrogen bond formed between the water molecules and the starch granules, okay, the ruptured starch granule. Okay, so two important factor for gelatinization. It must only occur in the presence of heat and water. Without heat and water, gelatinization will not occur. Okay, figure here shows the nice shape of the unheated starch granule. So this is a figure showing 5% of cornstarch that just start to undergo heating, okay. So water start being absorbed into the granule, okay, and the granule still clumping nicely, okay, because only the early stage of heating. So as the temperature increased to 40 degrees Celsius, more water is being absorbed, and now we can observe in the figure there, according to microscope figure, the granules start to separate, okay, between from each other, okay. So the granules start to separate, no more clumping. At higher temperature, as it increases to 65 degrees Celsius, more water is being absorbed, and now the starch granule begins to rupture, okay. So you can see some begins to rupture, okay, some still in the form of granule. And even higher temperature, 70 degrees Celsius, further rupture, okay. So further rupture of the starch granule can be observed here, okay, and then leakage, okay, leakage of the starch granule, okay, once the water is once the granules is ruptured, okay. So this graph shows what happened during starch gelatinization in terms of viscosity versus time. So at early stage here, okay, the starch granule is still nicely shaped, and then as the time increases, as the time increases as well as the temperature, now this becomes swelling because it absorbs water. Okay, further swelling as the temperature increases and time increases, and then rupture. Okay, granules rupture, and then upon cooling, okay, this stage here, some of the starch molecule reassociate to form a precipitate or gel. Okay, this process is called retrogradation. Okay, upon cooling. So gelatinization depends on one, the starch origin. Okay, so higher amylose content will result to stronger gel. Higher amylopectin content will result in more viscous starch paste. Secondly, gelatinization will depend on the water content. Okay, the higher the water content or more water is present, then higher gelatinization of the starch. And then the third factor is temperature. Okay, so temperature is important in order for gelatinization to occur. Without temperature, gelatinization is not possible. Now, what is retrogradation? Okay, during the cooling period after gelatinization. Okay, so the solubilized starch polymer and the remaining insoluble granular fragment tend to reassociate after heating, and this reassociate is termed retrogradation. So this is a process occurring when the starch chains start to reassociate into an ordered structure. So in its initial phase, two or more starch chain may form a simple junction point, which then may develop into more extensively ordered region, and ultimately, under favorable condition, a crystalline order appears. So if we refer back to the earlier figure of gelatinization, if you refer back to the figure, something like this just now, okay, the starch granule, okay, the formation of hydrogen bond between the water, okay, and the starch granule. Okay, so during the retrogradation, okay, this water molecule may exit, okay, okay, and the starch granule or the junction may come closer. That's why it will form a crystalline order. A very simple example I can give you is that when you cook rice, okay, once the rice is cooked, it's very sticky, right? Okay, very sticky. So we can say that has undergo gelatinization, because when you put the rice granule in your pot with the presence of heat, okay, and water as well, and it will form that rice, okay, that nicely eaten, okay. Okay, dimakan panas-panas. Awak letak beras tu dalam pot tu. Okay, beras tu consider as the natural state of the starch lah. Okay, bila beras tu dah masak, dia jadi nasi. So, nasi itu dah undergo gelatinization process. Now, you scoop out the rice, okay. Awak ambil lah nasi tu, you put it on the plate and let it stand for, let's say, 1 day. Biar 1 hari. What happened to your rice? It will eventually become hardened, right? Hardened. So there is a crystalline order, okay, because some of the water has escaped, okay, escaped. So that is retrogradation. Now, this short-term retrogradation is largely associated with amylose, okay, which reaches a limit in 2 days. Long-term retrogradation involve amylopectin, means it reach a limit in 40 days. So amylose containing starch will show greater retrogradation. Okay, for example, rice just now. Okay, high amylopectin starch, for example, waxy maize, will show no retrogradation even when frozen. Okay, another example I can give you is bread. Okay, bread, once it is freshly baked, it's still soft, right? Okay, but then when you let it, let's say 1 week or 2 weeks beside mold growth, okay, it will undergo retrogradation. Okay, okay, so this is the junction zone. Okay, you see here, not too large here. This is where retrogradation occurs already. Okay, during the gelatinization, the junction is very far apart from each other. To monitor starch gelatinization, we can see in terms of, or we can measure the viscosity as a function of temperature. Okay, so if you see in this graph here, um, we can see as the temperature increase, okay, the viscosity will increase rapidly, okay, due to the swelling of the starch granules. Once the granules burst, okay, then you see a sudden drop in terms of the viscosity. Okay, sudden drop due to the burst of the granules. And the pattern is similar in these two different starch source here. The first curve is potato, secondly is waxy corn. So potato will exhibit a maximum viscosity. Okay, so if you see here, around it actually should be around 4,000 barabender unit. Okay, barabender unit. So waxy corn will show a similar pattern, just that the maximum viscosity is lower. Okay, lower than potato. Now upon cooling, okay, from this period here, okay, 40 minutes onwards, we can see that both potato and waxy corn will exhibit a slight increase in terms of viscosity. Okay, here, okay, slight increase in the viscosity. Now, I have mentioned that in my earlier slide that high amylose content will lead to a stronger gel, whereas high amylopectin will lead to viscous starch paste. Okay, so on rapid cooling, okay, from this 40 minutes onwards, the viscosity of a starch paste will form along with mixing. However, for starch gel with high amylose content will form during this cooling period without mixing. Many quality defects in food products such as bread staling and precipitate formation in soups and sauces are mainly due to starch retrogradation. So what what does it mean by bread staling here is you will note the formation or the increase in term of the crumbs um, of cake or biscuit or bread once it has cooled down to room temperature. Okay, unlike when it's still hot after it is baked, it is more soft, right? Okay, but then when it cools down to temperature, it becomes um, hardened. Okay, uh, due to the retrogradation process. Okay. Um, Similarly, for precipitate formation in soup, for example, when you go to Pizza Hut and you order soup, okay, the soup when it cools down, you will notice the formation of a solid layer on the top of the soup, right? So that is the precipitate formation due to retrogradation of the starch in the soup. Okay. Um, So staling will begin as soon as the baking is complete and when the product will begin to cool down. Okay, and this is responsible by the presence of the amylose of the starch. Okay, amylopectin will also retrograde, but it's a very slower pace compared to amylose. Okay. Now the staling of the bread um, is due to the transition of the amorphous starch to a partially crystalline state, and that is what we call retrogradation or retrograded state. Okay, the amylose retrogradation or insolubilization may be largely complete by the time the product has cooled to room temperature. Okay, so means when the product has completely cooled to room temperature, then uh, complete retrogradation of the amylose. Okay, now amylopectin retrogradation believed to involve primarily association of its outer branches, and it will require a much longer time compared to amylose. So in simple term, we can say that retrogradation will not occur in uh, very high amylopectin uh, content of a starch um, product. Okay. So this staling process will occur with time once the product cools down. Okay, after cooking or baking, so on. Now, this undesirable retrogradation and staling in bread, especially between the time when the bread is baked and consumed. So due to this reason, understanding the different aspect of this staling of bread and the factors that affect this retrogradation and staling in bread will uh, has helped the bakers to make better decision in terms of the formulation or the ingredient or the process during the bread making. So therefore, polar lipid like surfactant properties, okay, polar lipid with surfactant properties means it has both hydrophilic and hydrophobic character, will help to retard this crumb firming upon retrogradation once the bread um, is baked. Okay, so the addition of compound such as glyceryl monopalmitate (GMP), okay, or sodium sterol 2 lactylate (SSL) is incorporated into the dough of bread and other baked goods in order to increase the shelf life, means to slow down the retrogradation and staling stage. Amylose chain, they are actually helical with hydrophobic interior part, and this hydrophobic interior part have the ability to form complex with another hydrophobic molecule. So therefore, polar lipid with that um, surfactant properties means it is both having both hydrophobic and hydrophilic character, can form complex with the amylose chain of starch. It can also form complex with amylopectin, but it's not as much as with amylose. Okay, and due to this reason, it can affect the starch paste and starch based food complex in one or more than one way of these three ways, which is the first one. The polar lipid will affect the process associated with starch gelatinization and pasting. Okay, so if you refresh back, okay, starch gelatinization and pasting involve the loss of birefringence, involve granular swelling, and then up to one point, the granule of the starch will burst and leach out the amylose. Okay, involve melting of the crystalline region of starch granules, and also increase in viscosity during cooking. Okay, this is what it means by birefringence. Okay, to refresh back, so it under normal light, for example, in this figure of potato starch, okay, only the spherical or oval shape can be observed. Okay, the birefringence can only be observed under polarized light microscope. Okay, like the figure on the right here. Okay, due to the light refracted in two different direction. Okay, so you can see the Maltese cross formation here. Okay, so this is what we call birefringence. Now going back to the how lipid can affect retrogradation. Okay, besides affecting the gelatinization stage, okay, at the same time, it can also modify the rheological behavior of the resulting paste. So the lipid, okay, can slow down the formation, slow down the retrogradation process, okay, because it has modified the behavior of the paste. Okay, so the upon cooling and mixing during the cooling stage, that is where the retrogradation will begin. So when it in the presence of lipid, it can modify the behavior, means it decreases the tendency of the formation of the retrogradation uh, period once the cooling stages begin. Okay. The third one is by inhibiting the crystallization of starch molecule associated with the retrogradation process. So means the lipid can at the same time inhibit the crystallization of starch molecule, okay, during the retrogradation process. Next, we move on to modified starch. Now, what is the purpose of modifying starch? Okay, it is done to improve the characteristic of paste and gel so that the paste can withstand heat, shear, or acid during the processing condition. And another one is to introduce specific functionalities to the modified starch. So starch can be modified either chemically or physically. So under chemical modified starch, we can have there are stabilized starches or cross-linked starches. And under physical modified starch, it is further divided into two, which are pre-gelatinized starch, which is cold water soluble starch, like pudding. Okay, pudding, the processed pudding that you can buy from supermarket. Okay, can form gel even using cold water. Okay, cold water is soluble in cold water. Another one is cold water swelling starch. Now, if we look at the characteristic of stabilized starch, which is modified chemically, and also cross-linked starch. Okay, for stabilized starch, it will have lower gelatinization and pasting temperature. Okay, means it does not need high temperature in order for the starch to be gelatinized, okay, and followed by pasting. For cross-link, on the other hand, this type of starch will need high exhibit higher gelatinization and pasting temperature characteristic, okay, compared to stabilized starch. For stabilized starch, the starch granules are easier to redisperse when pre-gelatinized. Okay, means the temperature is rather high, but it is before it reach the gelatinization temperature. Okay. And then the stabilized starch will produce paste and gel with a reduced tendency for retrogradation, okay, having greater stability, okay, improve in terms of freeze thaw stability and greater clarity. Okay, so that is the benefit of stabilized starch. For cross-linked starch, it would increase resistance to shear, increase stability to low pH condition. So these are all the factors of gelatinization. Okay, and then it produce paste with greater viscosity and stability. So you can see here, this is again a graph showing the three different sources of starch when it as a function of time and temperature, and the change in terms of its viscosity. Okay, so like I have explained in the earlier graph, okay, viscosity increase as the time and temperature increase, so it becomes maximum at this point here. So this is where gelatinization occurs, and then rapid decrease in terms of viscosity as the granule bursts, okay, and then upon cooling, the viscosity will increase. Okay, so start to increase for this tree, and you can see the different in terms of increase in viscosity for different type of starch. Okay, corn will exhibit the highest viscosity compared to crosslink and waxy corn. Okay, so means the crosslink, okay, the modified starch here, okay, will be in between the corn and the waxy corn. Okay, so you see the viscosity is improved compared to corn and also waxy corn. Okay, next we look at the freeze-store stability. Freeze-store stability is the ability of a product to maintain its composition and integrity after repeated cycles between freezing and ambient temperature level. Okay, means the food with starch-based food, okay, at a point it is taken out from freezing temperature and thawed at room temperature, and then you put it back into the fridge to freeze back. Okay, so means the repeated cycle. Okay, so retrogradation is very sensitive to temperature, especially low temperature. So low temperature will start the retrogradation process. Okay, so means this modified starch, okay, is not easily retrograde. Okay, even though it is it undergo this repeated cycle of freezing and thawing. Okay, next we move on to physically modified starch, which is pre-gelatinized or instant starch or cold water soluble starch. So this is the process involve starch that has been cooked and undergo pasting and then dried, okay, dried without excessive retrogradation, okay, and then can be partially redissolved in room temperature. So means it has undergo gelatinization process, has undergo pasting process. Okay. So these modified starch are used in dry mixes, for example, instant pudding mixes, which has the ability to disperse more easily because it has been pre-gelatinized. The next physically modified starch is cold water swelling starch, and this starch is made by heating starch in 75 to 90% ethanol by a special spray drying process. So the difference between this cold water swelling starch and the conventional pre-gelatinized starch previously is that in pre-gelatinized starch, the crystalline order and also the birefringence of the granules are destroyed during the gelatinization process. But for cold water swelling starch, the granules are still intact. So that is why when water is added to this starch, physically modified starch granules, they can swell, okay, as if they were being cooked. And this kind of modified starch are used in making gum candy. All right, next we move on to cellulose. Okay, cellulose, like a structure is shown in the figure. Okay, so it is high molecular weight. It is linear like amylose also, just that they are joined by beta 1 to 4 glycosidic linkage. And it is also water insoluble. So these are the cellulose properties. Okay, it is not digested, means no calorie, so it only acts as dietary fiber. And then powdered cellulose is purified for use in food products, okay, because they have little color, little microbial contamination, and in terms of flavor, it's negligible. So microcrystalline cellulose can be prepared uh, by using acid. Okay, so acid will attack the amorphous region of the cellulose, and then it will hydrolyze it. Okay, um, so what is left behind is what we call crystallites or fringe micelles. Okay, and this is called MCC, okay, microcrystalline cellulose. So this figure shows the crystallite formation, okay, the one in the circle here, okay. This is the crystallite formation, okay. Now, what is the use of this MCC? Okay, MCC is used as anti-caking agent or flavor carrier in cheese. It is also used as calorie reducer in baked goods. It is used to stabilize dispersed oil. It is also used to replace fat and oil in products like salad dressing and ice cream, and also to control ice crystal growth. Next, we move on to extruded gums. Okay, so when the barks of some trees and shrubs are injured, the plants will exude or will form a sticky material, and this sticky material will harden to seal off the wound and also to give protection from infection and desiccation of the tree barks and shrubs. And these sticky materials are called gum. Okay, so there are different type of gums used in food application, which are gum arabic, gum karaya, gum gati, gum tragakan. The use of these gums has diminished over years because of uncertain availability and also increase in terms of cost, okay, to get this gum. So currently only gum arabic is has important application in food. Now, where does this gum arabic comes from? Okay, it comes from acacia trees, and these trees are grown in the Sudan and other African countries only. So that is where um, the availability and cost comes from. Okay, so in the trees, this material seal off wound and give protection from bacterial infection to the tree barks. Okay, so the picture there shows the tapping of acacia tree. Okay, so means they have to wound, okay, wound the trees so that they can harvest the sticky material. Okay, so you see, for 2 foot times 2 inches strips of barks removed, okay, only about 20 to 200 grams is hand collected in the period of 4 to 8 weeks. Okay, so that is where the high cost come from. Okay, and the total production is only about 60,000 to 80,000 ton to supply to the rest of the world. Okay, so this picture here shows the gum arabic exudate, okay, after the tree has been wounded here. Okay, this is where the gum is harvested. Okay, and this is a close up of gum arabic. Now the structure of gum arabic is R, okay, R, D galactose, L arabinose, L rhamnose, and L D-glucuronic acid. And due to this reason, the molecular weight is very high, which is 250,000 to 1 million. And of course, the structure is very complex, okay, and having slightly acidic pH, which is in the region, in the range of 4.5 to 5. Now, why gum arabic is unique? Okay, because gum arabic has high water solubility, means it is easily dissolved when stirred in water, and the concentration of gum arabic can go up to 50%. Okay, if concentration is made more than 50%, then it will disperse and form something like gel. Okay, and this gum arabic is used as food encapsulation also. Now, what is the gum arabic used for? It is important in confectionery products where gum arabic is highly compatible with high concentration of sugar, so that is widely used in confection with high sugar content and low water content of product also. Example of confectionery products includes caramels, toffees, jujubes, and also pastilles. So in confection, the gum arabic prevents sucrose crystallization. It also emulsify and also distribute fatty components of food products, and also helps in preventing bloom formation or surface whitening. So what does it means by surface whitening? I can give you a simple example. When you buy chocolate, have you ever encountered chocolate with white solid on the surface of the chocolate? Okay, that is actually surface whitening, okay, formation. um, um, so when the Arabic gum is added to dairy products like chocolate, it will prevent the formation of this surface whitening. It is still safe for you to eat. Okay, it's not expired yet. Okay, just that probably in terms of physical appearance, it will not look um, uh, appealing, okay, for you to eat. Okay, so gum arabic is a very good emulsion stabilizer for flavor oil in water emulsion. So means it prevent the separation of oil and water. Okay, so addition of gum arabic will stabilize the emulsions. And this Arabic gum is choice for emulsification of citrus oil or other essential oil, and imitation flavors used as concentrates for soft drinks. Okay, so in the US soft drink industry consume about 30% of the gum supply, which act as an emulsifier and stabilizer to the soft drink. Okay, and lastly, used as flavor fixation, okay, in which it prevents oxidation, volatilization, and degradation to food products. And these are the labeling for gum arabic. Okay, you can see in the label, sometimes it's labeled as gum arabic, sometimes labeled as arabic gum, sometimes gum acacia, sometimes acacia gum. So they are actually all the same thing. Okay, with that we end our lecture on carbohydrate.